In this video, I'm load testing this battery. I bought this battery with my own money. Did get a discount on it. Was asked to make a review of it, which I'm doing. I made a previous video where I opened it up, showed the BMS, the construction of it, talked about the app, and in this video I'm doing load testing, but I also went over some of the charging specs, or how I would charge it. So if you don't want to see all that, you can skip ahead in the video and get right to the load testing. Hope you enjoy it. Okay, I'm finishing up my review testing of this Orient Power 12 volt 230 amp hour battery, and I wanted to go over some of the best practices. Well, first, it came 50-some% full according to the app, and I charged it 2 days. First day I put in 98 amp hours. I was charging at 20 amps. And the second day, when I finished up the charging of it, I put in 38 amp hours. So a total of 136 amp hours. And it says that it holds 230 amp hours. So if you take some of the inefficiency of the charger, and maybe I overcharged a little bit, I mean, that's about right, because it was 50-some%, 115 amp hours it would take, but it might actually hold more than 230 amp hours. That's why 136 went into it. Anyway, it's full, and I wanted to go over some of the how I'm going to determine what to charge at. These are LiFePo4 cells. So the top you ever want to charge each cell to is 3.65 volts. That's the maximum. You don't want to ever go higher than that. You can ruin the cells. And that's what the internal BMS in here will do. It'll cut it off if it goes higher than this. That's how it protects it. But anyway, there's 4 cells in there. 3.65 volts times 4 equals 14.6 volts. So that's the highest you would ever want to charge it to. 3.5 volts per cell, that's 14 volts. And 3.45 volts per cell, that's 13.8 volts. And that's what this is what I charge my other lithium batteries to, because this number here, 3.45, is about 99% full, and it stays away from the top. And the relationship to this, it's like, well, how do you pick which one of these to charge it to? This is what most battery chargers would call the absorb. That'd be the top voltage and absorb. Different chargers and inverters and things have different nomenclature they use for that. The old-fashioned way was that's absorb, so it's the top. And the relationship is that if you charge to this, your absorb time is going to be shorter, like 0 minutes. So if you bring it up here, it's going to charge basically faster. If you have that big a charger, they can cram that many amps into it. If you go here, then your absorb time's like just 3 minutes or so. You know, it's going to be full. And the absorb time, I'll explain that. But anyway, so I charge to here, 3.45 volts times 4, 13.8 volts. So between 13.8 and 14 volts is around where I would charge it to. And I brought it up to about 14 volts when I just charged it. The absorb time is going to be longer. So here, probably like, 15 minutes, actually 5 minutes to an hour. 15 minutes is usually what I to an hour long. And well, why would you want it to be that long? Is because this is set up to balance. The BMS in here is set up to balance. It'll start balancing the cells, because ideally you want all the cells, all 4 cells, to come up exactly the same voltage and the same time. And if you have like one cell at this 3.5 volt, 4 or 5 volts, and one cell at this, they're going to add up to the voltage here, but they will be out of balance. So the BMS in here is going to, it's called a passive balance. It'll bleed off some of the voltage to try and equalize these two and balance them. And this is the balancing point according to the specs. 3.45 volts with a voltage differential greater than 50 millivolts. So it's not, they come up to 3.45 volts. It's not going to balance anything unless the difference between 3.45 volts is greater 50 millivolts. And the math on that is here. 3.45 volts plus 50 millivolts equals 3.5 volts. So, and here's how you do it. Here's some of the math you can do on it. If you do the conversion, 3.45 volts equals 3,450 millivolts plus the 50 millivolts equals 3,500 millivolts. You divide that by 1,000 and you get 3.5 volts. Or you take that and multiply it by 0.001, you get 3.5 volts. You're just moving the digit over 3 places. 1, 2, 3, 3.5. And here's the, you learn this, and when you're converting, 1 volt equals 10 times 3 millivolts. That's 1,000 millivolts. 1 volt equals 1,000 millivolts. And you'd multiply it by 10 to the 3rd power. And 1 millivolt equals 10 minus 3 volts. Minus exponent, 10 to the minus 3 power, I should say. And if you did that, you move the decimal over 3 places. 1, 2, 3. See, you get 1, 2, 3 negative. That's how you get your 0.01 volt, which is 1 millivolt. Anyway, and then usually on controllers you'll have a float setting, and well, I should go back to this rating here. Says 12.8 volts. So if you charge it, I should check the voltage now, but it's probably just sitting around the resting voltage is going to be like 12.8 volts, and that's the nominal. Well, that's the nominal voltage of the cells. 3.2 volts times 4 equals 12.8 volts. But when we're charging, we get to the top here, and then we keep it for however much absorb time we want. And I was saying, how long do you want to leave it? Well, if you have cells that are different, so one of them's 3.45 volts and the other is 3.5 volts, and the other two are somewhere in between, they need time to balance out. So that's why you'd have a longer absorb time on there. If they're all balanced, you can have a real short one. You can see that in the app if they're unbalanced. Anyway, that's how that works. And I was going to say here, so you got your absorb setting. That's where it gets to the top, and when it's done absorbing, so 0 minutes or 3 minutes, whatever you have it set for, you want it to go to float. Most controllers have a float. So the float voltage is like this, usually this, 3.35 volts per cell times 4, that equals 13.4 volts. So that's where I would set the float for, because at the float, basically it's not going to charge the cells anymore, but it'll let the controller will still provide all the loads. So let's say you have, 50 amp load on the battery, and you have 50 amps coming in from the solar panels. It float at this voltage. The controller is going to let it take the 50 amps to the loads, but it's not going to put any more power into the battery cells. Because basically with these lithium batteries, you just want to charge them once a day full and then not charge them anymore. So this voltage here will let them not charge anymore till the next day. Then you'll go through the cycle again. On a typical solar system, that's what you do. So I think I had one more sheet. What was that about? Oh, that was the balancing. So the balancing only starts. I sort of explained that it only starts when one cell is 3.45 volts and another cell is 3.45 volts. Another cell has to be at least 3.45 volts. That'll be 50 millivolts higher, or it's not going to balance anything. So if another cell is 3.49 volts, there's no balancing going on. It has to be 50 millivolts more for one cell or more cells. It could be this is 3.46 and this is 50 millivolts higher. It doesn't matter as long as this is higher than this. This is higher than 3.45 plus 50 millivolts. This one's 50 millivolts higher. It'll start balancing. Hope that makes sense. So these were in pretty good balance. When I charged it, I looked at the app and they didn't need any balancing. They were like maybe, I don't remember exactly now. I didn't make video of it, but it was like 20 or 30 millivolts difference, which isn't bad, So when they're at the very top, when they're at the very top voltage here, so they're pretty well balanced. Anyway, I wanted to talk about some best practices for 12 volts solar, any solar. I borrowed some cables just to do the testing, and these cables, these terminals here are copper. I've been trying to shine them up because bare copper will get somebody put a little solder on there, that's why it looks silver. But bare copper will oxidize. You can see on this one it's not as shiny, except for where someone put that. So I started sanding them with some fine sandpaper to get that dark oxidation off, because that acts like insulation. You want it shiny so you get all the power transfer through that. So that's what I'm going to do. The other thing I'm going to do is put a breaker in. I just had this one around. The other thing, ideally, you want these cables here. You want these cables to be the same length so that the resistances are the same. And I'm going to put a breaker in there just for safety, for test, and I can shut it off. So this breaker here is rated for 250 amps and the maximum volts is 125. And you can see the hertz rating is DC. There's no, so it's not an AC breaker. And it's labeled line. I think these are non-polarized, but they got them labeled line and load here for these terminals here. It's a real big giant breaker for an inverter. So it's a little, this has a 200 amp load. So you could use this breaker as long as you size your you want to size your cable big enough. But this is what I'm using, this stuff that I have now. This is like 2-0 wire. And that's what I'm going to be using. And I'm going to put it on this 1.5 kilowatt inverter. And then plug some loads in. I got this terminal block, or this power strip on here. But of course, I'm only going to be able to do like trying to remember the certain amount of watts on this because it has a built-in 15 amp breaker. And 15 amps times 120 volts, you can do the math. It's what, like 1500, 1800 watts or so, I think. So that's all I can do here. So 1800 watts. Well, this is capable of a lot more than that. Anyway, I'm going to hook things up. Oh, the other best practice is put some red tape on your positive side so you don't confuse things when you're hooking things up, because there's a huge amount of energy in here. You don't ever want to short this and this, because whatever wire you put in there is going to get red hot fast. And the other thing is, if you're using metal tools, put some tape around them, around the handle, so that if you accidentally dropped it, like if you're using a crescent wrench, you accidentally drop it, it's not going to short, or if you touch something else. So be real careful when you're using this amount of potential energy in one of these batteries, or any battery really. You don't want to short circuit. The only thing I forgot to mention about these terminals is that some of them, you can get some that are bare copper. It's hard to see at this light, but you know, they're bare copper. You can get these ones that are tinned. The tinned ones aren't going to corrode and get oxidized like the bare copper ones will. If they do, they take just about nothing to clean off. So if you get cables, don't get bare copper ones, or if you do, you can get them nice and shiny and then put some antioxidant on them, or cover them with something so they don't, because it's like you're going to lose some of your power through a bad connection if it oxidizes at 12 volts. We don't worry about things like 120 volts. We don't ever worry about these, because 120 volts, the resistance on a bad, like oxidized copper connection isn't as much. Ideally they'd be clear, but when you're down at the lower voltage, then you want to make sure they're really, like 12 volts, you want to make sure they're really clean for your best power. Otherwise, if you get a high resistance and a lot of power, they're going to warm up and melt things if it gets warm enough. Okay, here's my temporary setup, and this is just an experiment. It's not best practices for this, but it's best practices in a way. I have the inverter hooked up. Positive goes through this breaker, which is off. I made the first connection I made was from the negative of here to the negative here, and then my final connection I made was the positive, but I made sure this was off. If I didn't have the breaker in here, if it was on and I just hooked this up, you might get a huge spark, because if there's capacitors in the inverter, especially a lot of the newer inverters, they have big capacitors in them, and you would get a huge spark, and it would make a loud noise, and it would scare you pretty bad. You'd think something bad really happened. That's because the capacitors can just charge an instantaneous amount of power really quickly. So it's a surge. So better to have the spark in here than here when you're hooking it up. So that's why I did it that way. And I made sure, you can see I got my metal tool, which if I was to bump this, you'd have a short, but this is kind of short here, so it won't touch across. You still want to be careful about this stuff anywhere. Oh, I guess I could turn it on and see what happens. I've never turned this inverter on. No idea what's going to happen here. So let's give it a go on film. It's kind of scary. Oh, something clicked in it. I saw the lights go on and then something clicked off. So So maybe this inverter won't work. There's no light on there now. Let's try it again. Well, that doesn't sound good. Let me investigate. Okay, I investigated. And then I thought it was junk and I'll scrap this thing out. And then I saw this little button here. On off button. Look at that. It works. I just had to push that little button to turn it on. It's providing AC here. So I'll put some loads on it. I'm going to put a lamp meter on the positive here so we can see how many amps it's drawing out of there. Here's the meter I'm going to use. I put it on the 100 amp range here, and on this meter you can see it's AC. It's an AC-DC clamp meter, but you need to select DC. There, now it's in DC mode. The other thing is, when you're in DC there's a plus and a minus, so you want to have this going to the positive side, which will be the battery. First you have to zero it out. You hold this here, you press the 0 button, so that zeroes it out on DC. You don't have to do that on AC. And it's just big enough to go on here. So I will put a load on there and we'll see what happens. This current should be, let's see if it zeroes out when I take it off. Yeah, so the current on there now is what the inverter is using for idle current, which is, if I go to different range, so 400 taking almost, so it's 400 millivolts, or milliamps I mean, so not quite half an amp. So that's how much it takes just for running the inverter. You could probably get better resolution. If I go to this other scale, go to 20 amp range here, we'll go to 2 amp and we'll get good resolution. 2 amp scale. Then of course we got to go back here and select DC again, and we need to zero it out. Pretty close. Let's put this on here. Yeah, so it's taking a half an amp. The resolution on the higher scale doesn't show it as well, but it takes 526 milliamps, so over half an amp just to run it. I'll turn the button off on the inverter. Should go to 0. It doesn't go to 0. That means it has a, I'll turn the breaker off. It has a load even when, well, now we're not all zeroed out. Let's try the zeroing out thing again. Okay, let's get it on there. It's not going to be perfect. I'll turn the breaker on first. Well, it's showing it's drawing power without it even on. Let's turn it on. I'll push that button on the inverter. Okay, well that's what it says. I don't know how accurate that is, because if we take this off, we zero it out, then we put it back on. Yeah, takes over half of an amp. So before I put any loads on, I got to put it on a higher scale. Back on 100 amps. DC range, zero it. Well, I got to put it up here to zero it. There, it's showing 0.4. So that's the difference you get in resolution when you go higher. So it might be 0.4499. It's going to show 0.4 on this. So I will get a load put in here and we'll try see what it does. I'm going to put this space heater on. The rating on the space heater says, I don't know if you can read that. Right here it says 1500 watts. 12.5 amps, that would be at 120 volts, and 1500 watts should be the same between both AC and DC side. So we'll try it out and see what it says. I will put this on where does it say? I think it's got different settings here. We'll put it on high so it gets as hot as possible. And let's see what it does. When I turn, it's plugged into the power strip here, and I'm going to turn it on here. Oh, I'm taking more than 100 amps out, and that's why my meter's beeping overload. So this meter isn't going to work. But I think I might have another meter. I'm going to go look for it. That goes higher. Okay, I have another meter. This Excel Tech one goes up to 400 amps. So we'll get this set up. 400 amp range. And then again we have to select the mode. It turns on in AC, so we want it to be DC. Now it's on DC. Then we need to zero it, and this thing too has a plus and minus side. Doesn't say plus and minus though, does it? I believe that's what this means. Well, that's non-contact voltage. I don't know. I'm going to assume this side is plus. I'll have to look in the manual if I still have it. It won't make a lot of difference, but it makes some difference if you put it on backwards. So anyway, let's finish zero this up. Here's the zero. I think you have to hold this one down to zero it. There. Then we'll put it on. It's showing about the same thing, 0.4 amp, just idling. And I have the voltmeter set up too. See if I can get them both in the same shot. So now I'm going to turn the load back on. Oh, I got it unplugged. I'm like, why didn't it go on? I unplugged it. Let's try that again. Okay, turn it on. There you go. That's why we tripped the other meter when overloaded. It's 155 amps, and the voltage dropped to 12.6. So that's a pretty good load on there. I'm going to let's see, if I take this and multiply it by this, it'll give me the watts. Okay, I totally forgot that I had the BMS, the Bluetooth BMS. I was so excited about getting all this stuff working. I forgot. I can look at it on here. So let's compare. 13.22 volts. This one says 13.249. So pretty close. Minus point. See how that's flickering? It's because that inverter's going to sleep mode. It goes on and off to save energy. But anyway, it says 0.508 amps, 508 milliamps, and this one's showing same thing, more or less. So let's turn the load on again and see what it does. I got all 3 meters agreeing for a change. 100. There we go, 155 amps. This says 150. So they're off a little bit. 12.57. That one's off a little bit too. 12.54. 12.743. Don't ask me why they're all different. Interesting. I have another space heater. I'm going to see if I can overload this breaker. I got this space heater. Oh, this is kicking out some heat. There's no labels on here. I think it just goes like off, fan, low, high. Even though whatever this cheap thing, the labeling didn't stick on there. So I'm going to plug this one in too. Let's see if we can this thing will overload at 15 amps. But let's see if it changes. I'll turn the fan on it now. Turn the fan off, turn the fan on. Doesn't make as much difference. Now I'm going to turn it on low heat. That could overload it, but we'll see what happens. That didn't seem to do anything, did it? Turn on high heat. Since I got this from the junkyard, oh, it just feels cool. Maybe this doesn't work. Let's try it on the high heat setting. There it goes. Oh, it kicked it off. It kicked the inverter off on overload. So, that ain't gonna work. I didn't see, I'm going to do it again because I didn't see what, I didn't see how much it surged up to. But everything's off. It might have, if it went over 200, well there's, oh yeah, it kicked off the discharge on the, it says off. It kicked off the BMS, so it must have gone over 200 amps. Let's try it again. We'll have to wait for this thing to reset, I guess. I don't know how to do that. That doesn't let me do without a password. Maybe it'll do it on its own. I'll turn the load off totally. That's interesting. I wished I would have seen what that surged up to. I didn't have the camera on it, I don't think. We'll try it again when the discharge MOSFET is off. So no power coming out of that. No, there's power there. Right? Oh, I guess they said there's always that power showing when the BMS is off. I wonder if I turn the BMS off and back on, if that'll reset it. I might have to rehook up the app. There, okay, it went on. So we should be back in business. I might have to reconnect it though to get this to show. Oh, wait a minute. Let's back off. Oh, it's on. 13.19. There we go. And it's reset, see? My meter's beeping like it's going to shut off. Let's do that real quick. Okay, this is back on. Discharge MOSFET's on. I had reset it. My battery went dead in the camera, so I had to get a new battery. This is all ready to go. I'm going to turn the inverter back on. I'll turn the loads off. Turn this back on. There it goes. Press the on button. Turn it on. There we go. You can hear it humming. Oh, wait a minute. We got a load. I thought I turned it off. Oh. Because I had the load on instead off. Okay, let's see what happens here. I got the second heaters off. This one's on. Here's just the idle current of the inverter. Idle current means what it takes when it has no load on it. Okay, turn the first space heater on. We got our 155 amps. Let's see what happens. I will turn the second one on. We'll see what it sort of goes up to. This has a hold on it. Peak. Oh, min max. I want it on max so it'll capture it. I can't read it. Let's see if that's the right one. But we'll watch it on this. I'm going to turn that second heater on. We'll see what happens. There. That was it. I saw it go over 200. Went over 200 amps. Shut off the discharge MOSFET. This one didn't capture. I didn't have it in the right range. Oh yeah, it did. Well, 198. So yeah, anyway, we got our 200 amp load on there to test out the 200 amp capability of this. And it works. And it does shut off. I didn't notice I'll have to look back in the video and see how much the voltage dropped when it went up to 200 volts. So I don't know. I can't answer the question of if this will reset itself after time, or if you have to turn the BMS on and off to turn the load back on when it overloads like that. Maybe I'll just let it sit for a while. Well, you can see it shut this time it really shut the power off. There's no power at all on there. On the battery. It's right down to no volts, 1 volt. Anyway, that was a successful test of this battery. It will put out 200 amps. And it will protect it if you overload it. Okay, again, this just went on by itself. I guess there's a timer on it, or maybe something in the BMS has to cool off. As the inverter turned back on. Inverter's on. I'm going to turn I got the one overload off. I'll just turn the one on. You just have this on, and I got this on high. And it says 150 amps times 12.8. And if there's enough light in here, this calculator would work. I'll do that calculation. 12.8 12.75 times 149. Okay, I just multiplied the voltage times the current, and I came up with this. 1870 watts. So, what does this thing say it was? I can't remember. 1500 watts. You got some inefficiency of the inverter, and it's supposed to be a 1500 watt inverter, so maybe it does more. 1500 watts out, but it takes there's some inefficiency in it. It's not 100% efficient. So anyway, battery's doing a pretty good load. I guess if you can't get much of a bigger inverter than 1500 watts on this, maybe a little bit bigger. So that's it. That was the peak. That was the peak. Here's what it's doing now. 143, 147. There you go. That's my review load test of the Orient Power 230 amp hour battery. Just for a follow-up, I did some math. We had 195 amps, and if you multiplied that by 13 volts, it drops to around that, or 12.8. That's 2500 watts. So I guess you could theoretically put a 2500 watt inverter on this battery and stay under the 200 amps. Of course, that would be with just resistance loads, and you're not taking into account the inefficiency of the inverter and the battery, your cabling, some drops you'd have. Anyway, 1500 watts. The inverter I was using divided by 120, that's 12.5 amps. So that's kind of what they rated on, because typical circuit, 15 amp circuit in a household, they don't usually go over that for most appliances. 2500 watt inverter divided by 120 volts. Of course, I'm using US voltage, 120 volts. That's 20 amps, so that's a standard 20 amp circuit roughly. And 15 amps, the full rating of 15 amps here in the US times 120 volts, that's 1800 watts. So you see things advertised as being able to take 1800 watts, because that's the max anyone would want to go on a 15 amp circuit. So that's how that math works. And then you can throw some of these ratings out. If you plug in a motor in, you get a surge that's going to go up a lot higher. It isn't going to work on some of these, or it's going to go over this. So if you had a motor you plugged in, it might make this jump up higher. It's under 95 amps, and then it's going to cut out that inverter. I mean, the BMS 200 amp limit will be reached. Cut it out, even though you have a 2500 watt inverter, let's say, but the inverter says it can surge to like 4000 watts. So you plug a motor in, it's gonna kick it off. So better off sticking to like a maximum 1500 watt or maybe 2000 watt inverter if you really want to push it. And then I didn't do the calculations how long that battery would last if you were running full loads. I can do that. Okay, I did this calculation. 230 amp hour battery divided by 195 amps. If you were to take the maximum out, of course, not 195 because you'd want to stay under the 200. Then that would last you 1.17 hours. But in reality, you can't get that much out of it, because you're not going to take 100% out of this battery. Maybe you can get, if you're lucky, get 80% out of it. So multiply this number by 0.8. So, I mean, it'll run a big load, but you wouldn't want to run it for too long. And of course, the voltage on the battery will drop some too. So that helps anybody who wants to know how long it'll run something. But if you just had a small load, you know, like 3 or 4 amps, it's going to run it for quite a while. These are the extreme numbers. Okay, I just did the numbers for more realistic. 230 amp hour battery times 0.8, that would be 185 amp hours, because you don't want to take, you're not going to go below the 20%. You'll take 80% out of it. So you realistically are looking at something more like extreme 185 amp hours. And if you were running 5 amp load, divide that by 5 amps, you'd have 37 hours. So people ask how long it'll run, like a refrigerator or whatever. It could run it for quite a long time, but even with this number, you still need to factor in the inefficiency of the inverter, which might only be 90 or 95%, depending, you know, what inverter you have. So you won't even get this many hours, because you're going to lose some of it in the inefficiency of the inverter. But that's pretty good. I mean, you should be able to run a pretty good load for a whole day on that one charge, if you wanted to take it down all the way to 20%.